right, so we're going to go over homework number 3. This is over related rates and various theorems. So number 1, circular conical reservoir, vertex down, has a depth of 20 feet. So we have dimensions of our cone here. Depth of 20 feet, radius is 10 feet across the top, or just the radius. Water is leaking out so that the surface is falling at a rate of 1/2 feet per hour. We know that this is not referring to volume because the units here is just a one-dimensional unit, feet per hour. Surface is falling, so if surface is falling, we can think of that as height related. So we know dh dt, based off of that statement, is involving that 1/2. But it's falling, so we know that the height is decreasing over time, so we want that to be a negative rate, negative 1/2. Okay. The rate in cubic feet per hour at which the water is leaving the reservoir when the water is 8 feet deep is. So we have this moment in time when h is 8 feet, which we're not going to use until the end. We're not going to use this until the end. So save this information. To use at the end. Okay, do not use in the beginning. We're looking for dv dt. So that's our goal here. Now, usually with cones, what happens is that our volume formula is going to be, there's just too many variables on the right side. And so this volume formula will be given to you. We have radius and height, and the purpose of similar triangles is so that we can replace one variable with the other so that we can have a clean derivative without having to deal with multiple variables. And also because if we were to find the derivative using product rule, we're going to end up with more information than what we have, or more variables than the information that's given to us. So what we can do is we're going to kind of do a cross section and just focus in on this portion of our triangle. We have the water level that's changing, and the water inside the cone tank is going to form its own cone-shaped. I can set up proportions here. I can say the radius of the small cone is to the radius of the big cone, as the height of the small cone is to the height of the large cone. If I do cross product, I get 20R is equal to 10H. Divide both sides by 20. I get R is equal to H over 2. And the reason that I want to solve for R is because I have everything given to me in terms of H. So naturally, things will just work out cleaner if I just follow along the path of H. So if I can replace R in terms of H, then I'll be able to go through this problem, the path of least resistance, and just if I have everything in terms of H, naturally, I'm just going to have H is ready for me to use, or H variable related values ready for me to use. If I solved in terms of R, I can still get to the answer, but it's just a little bit more substitutions at the end. So I'm just looking ahead to see what's available and trying to streamline my steps. So if I solve for R, I get R is equal to H over 2, or 1/2 H. So I'm going to substitute this information in for R. So I'm going to rewrite my volume equation, get it down to one variable on the right side so that I have an easier time with my derivative. Replace R with H over 2. Clean this up. h over 2 becomes h squared over 4 times h. So I'm going to push all the numerators together. I'm also going to push all the coefficients together. So the 3 and 4 becomes 12. I can rewrite this as pi over 12. And then h squared times h becomes h cubed. So now I'm ready to find my derivative. Okay. V becomes dv dt, h becomes dh dt, so v becomes dv dt. Pi over 12 is a coefficient, that's just not going to go anywhere. H cubed becomes 3h squared. And then we need to attach a dh dt because we're asking for h's derivative. So now we have our derivative, and now we have everything that we need to plug in. So I can replace h with 8. Now I can use 8. I don't want to use 8 before this moment. Sorry, I meant to write 8 feet, but I just put a t there. So okay. Replace h with -1/2. Replace h. Replace dh dt with -1/2. Replace h with 8, and that should allow me to solve for dv dt. I do a little bit of cleanup here. I have 64 times 3 divided by 24. And that's going to get me all the way down to 8, -8. Pi is going to remain. So -8 pi. And my units is, my volume is in terms, is a cubic unit there. So cubic feet. And then time unit is hour. So cubic feet per hour. All right, number 2 is not a cone problem, but it's a cylinder problem. The formula is very similar to cone, but it's a lot easier. And the reason that it's easier is because if we can imagine there's a certain water level inside our cylinder tank. As the water rises or falls, the difference that makes this easier is the fact that as the water level falls in the cone, the radius is changing and the height is changing. But as the water level is increasing, decreasing, the height changes, but the radius always remains 5, right? The radius is not going to change, which makes this an easier problem because there's no need to hold on to our radius variable if it's just a constant all the way through. So at the beginning, we can simply replace our radius with a number, whereas with cones, we have to hold on to our radius a little bit longer, find a replacement for it using similar triangles. I think the mistake I see students make here is sometimes students want to force a similar triangle into a cylinder problem because we're so used to doing it maybe enough. We've seen this quite a bit here. We expect it to apply for something that has a similar formula, but there's no triangles here. Okay, so there's no need for similar triangles. Okay, not for cylinders. Okay, let's gather some information here. We have a cylindrical tank with a radius of 5 being filled with water at a rate of 3 cubic centimeters per minute. We know that is referencing volume. So dv dt, and water is being filled, so we know it's going to be a positive rate. So I'll say dv dt is a positive 3 cubic centimeters per minute. How fast is the height of the water increasing? We see the word height, but we see rate of change involved, so we know we're looking for dh dt. All right, let's see what we can do with our volume formula. We talked about how the radius does, as soon as we know what the radius is, we can go ahead and make that substitution. There's no need to hold on to that r variable. Okay, we're looking for dH dt. We have dV dt. We know we have to involve derivatives, so we'll jump into that process. So V becomes dV dt. 25 pi is a coefficient. That's not going to go anywhere. But then H becomes dH dt. And then we're going to start making our substitutions. So dV dt gets replaced with 3. dH dt is what we're looking for. Right, divide both sides by 25 pi, and we're able to solve for dH dt. Three over 25, can't reduce that, but the pi stays in the denominator. Units of measure. Height is a one-dimensional unit, so centimeters. Time is minutes, so centimeters per minute. At number 3, we have a differentiable function. F of 0 equals -4 and f of 10 is equal to 11. Which of the following must be true for some c value in the interval from 0 to 10? All right, so it says f prime of c is equal to 0 since extreme value theorem applies. We know extreme value theorem is ultimately after a max or min. Is not necessarily going to guarantee a slope of 0. Okay, so extreme value theorem requires testing of critical points and endpoints to find the max or min, and that's not the goal here. So this is application, or EVT finds absolute max and mins. So that's not the right application there. Part B, mean value theorem. Okay, it's possible. Mean value theorem, if our function is differentiable, I can guarantee a slope between the endpoints. So I think mean value theorem does apply. So let's see what mean value theorem says. Mean value theorem says change in my y value over change in x. So I'm just going to do mean value theorem is f prime of c is equal to f of b minus f of a over b minus a. My a and b values are 0 and 10. So make our substitutions there. F of 10 is 11. F of 0 is -4. So 11 minus -4 over 10 minus 0. Okay, so 15 over 10, we can guarantee the slope. And we see that this is a better match with C than with B because it looks like the sign is not matching up for our answer for that we found. So that's a match for C. We can guarantee that whatever the slope is, the slope being 15 over 10, which is 3/2, we can guarantee the slope somewhere along the curve. Okay. Fourth option is not correct because intermediate value theorem does not involve derivative. It just wants to know, is the graph going to cross some value between the endpoints? And that's not, the description doesn't match here. All right, number 4. We have a function provided f of x on the closed interval of the following interval on which can mean value theorem be applied. So mean value theorem has to be on an interval with no asymptotes and no holes. So we have some issues that we have to kind of work around, right? So mean value theorem is only going to apply if it doesn't span across these asymptotes. So we know there are vertical asymptotes at x equals 4 and x equals -2. So we know that our for mean value theorem, our domain is only going to be active in this interval. So between these values or around these critical points here. So from -infinity to -2, from -2 to 4, and then from 4 to infinity. So it has to live in this region in order for us to have a function that's differentiable with no breaks in the graph. So let's look at our options here. From -1 to 3, because f is continuous and differentiable from -1 to 3. So we see that there's an issue at -2 and 4. So looks like -1 and 3 is going to be safe. We're not going to. It's going to be within this interval, right? So we're safe. This is a valid interval there. From 5 to 7, that's also safe. That's safely within our interval there. We can keep that. But from 1 to 5 is an issue, right? If we go from 1 to 5, it's going to have to cross through that vertical asymptote. There's a break, and because there's a break between 1 and 5, we can't apply mean value theorem in that interval. So only answer choice 1 and 2, C. All right, number 5. We have selected values of our function. Which of the following statements could be false? Selected values of a continuous function. So we know that graph is continuous, but it doesn't say anything about differentiable. Okay, but may not be differentiable. It doesn't specify that, so we need to take into account that there could be sharp turns along this graph. It doesn't specify that it's a smooth curve. So part A says by intermediate value theorem, there's a value such that f of c is equal to 10. Okay, it says could be false. Okay, could be false. So we have a y value that's one endpoint being a y value of 1. We have the other endpoint being a y value of 31. So if it's going to go from 1 all the way to 31, that graph has to cross through a y value of 10 somewhere between, right? So this is definitely a true statement, and it's continuous, so we know that we can guarantee intermediate value theorem. Okay? So we're asking for a statement that could be false. This is a true statement, so we move on. By mean value theorem, we can guarantee that there's a value such that f prime of c is equal to 10. So can we guarantee a slope of 10? Well, let's figure out what the slope is between the endpoints, or between these 2 points. Right, so change in y over change in x. So I say 31 minus 1. Over 5 minus 2. Now this does give us 10. Okay, that does give us a slope of 10. But here's the issue: is that mean value theorem requires our differentiable notation or impact. It needs to have a statement about differentiability. So there's no statement about differentiability. We can't guarantee that mean value theorem is going to apply. So this could be false. Okay, could be false because we may be looking at a graph with a sharp turn. Does not specify differentiability. So this is a could be false, which could be our answer. Okay, but let's keep going. By extreme value theorem, there's a value such that f of c is less than or equal to f of x for all value between 2 and 5. So extreme value theorem, we can guarantee that whatever f of c is, EVT only requires continuity. So extreme value theorem we can apply because we have the conditions set up for it. This statement is also extreme value theorem. And so both these have the required conditions. The only thing that doesn't have the required condition is B, so our answer choice is mean value theorem. All right, number 6. Let the function be cosine of natural log of x squared plus 1. On the closed interval, how many values satisfies the conclusion of mean value theorem? So mean value theorem, we're going to have to go through our formula here. Let me write this above. So we have our endpoints 0 and 8. I'm going to insert them in. But I do need to find order pairs at these points. So I do need to find f of 0, and I need to find f of 8. So they can simply be inserted into the function here. We can use our calculator for that. So I'm going to enter my function into y1 so I can just call it and not have to enter this every time. So cosine of natural log of x squared plus 1, close parentheses twice. Make sure that I need to be in radian mode. If I do vars, y vars, scroll over, function y1, I can find y of 0, parentheses 0 is 1. I'm going to find my y value at 8, so vars, y vars function. It's going to give me a y value of negative 0.512. I do change in y over change in x, so I can find my slope. So change in y over the change in x. Clean that up in our calculator. We get negative 1.512 over 8. And that just gets us to be negative 0.189. So we want to figure out when is the graph of f of x going to have a slope that is exactly negative 0.189. So we need to find f prime so that we can actually solve for x. So let's find f prime. So the rule for cosine of u is negative sine of u times u prime. So cosine becomes negative sine of u. This whole expression is my u value. Times u prime. Now to find the derivative of natural log of x squared plus 1, we have a separate rule for natural log, which is u prime over u. So this portion is my u value within my natural log. So x squared plus 1's derivative is just 2x over my u value, so x squared plus 1. So we want to find out when is this derivative equal to this value. Right, so we set them equal to each other. I'll clean this up a little bit. Negative 2x sine of now the easiest way to solve this messy expression equation, we're going to, I think you use numsolve, but I'm also going to use a calculator. I'm going to bring everything over to one side, set equal to 0, and that way I can just graph an expression and then look for the x-intercept. So I'm just go ahead and move that 0.189 over. So let me enter that in here. Make sure again that you're in radian mode. I know I'm looking for a value between 0 and 8, so I'm just going to do zoom 6, see if that will show up. Look for my x-intercept there. I'm going to just adjust it so I can get a little bit closer view here. So window, I want my y value to not go as high as negative 10 to 10. I'm just going to make it go from, let's say, from negative 3 to 3, just so I can get a closer view of that x-intercept. It's asking for how many values. So how many values, how many x-intercepts do we see? Well, we see one x-intercept there. Maybe even make it where I don't have to look at values all the way to negative 10. I'm only going from 0 to 8, so maybe I just want to see a little bit around my boundaries here. So there's 1. There's 2. So I only have 2 x-intercepts. Yeah. So we didn't have to find the value. We just have to find how many intersections there were, so we just needed to know that there were 2 x-intercepts. All right, number 7, we have a related rates here involving trig, so trig related rates. In the figure shown, a hot air balloon is rising straight up from the ground, tracked by a television camera from a liftoff point. At the moment that the camera's elevation is pi/6, the balloon is rising at a rate of 80 feet per minute. At what rate is the angle of elevation changing at that moment? So we know that we have to involve some d theta dt. What is rate of angle of elevation? So that's ultimately our goal. But with trig related rates, we always have to start off with some trig equation, right? So either sine, cosine, or tangent. And based off of what's given to us here, we have theta, we have opposite, we have adjacent. So we're going to use tangent. Tangent is going to be our starting point. We're going to have to find the derivative here. So I'm going to rewrite this tangent theta, same thing as 1 over 300 times y. Just makes it easier for me to do power rule there. So let's just go ahead and find the derivative. We know tangent of theta becomes secant squared theta d theta dt. One over 300 stays, and then y becomes dy dt, right? With related rates, time is going to be our independent variable. So it's going to impact every variable in our problem. The theta becomes d theta dt, and y becomes dy dt. So we have, they tell us that the angle is pi over 6. So we can, actually, we're going to be able to replace all of the theta with pi over 6. So in this case, we are given theta. Secant squared theta, that's the same thing as 1 over cosine of pi over 6 squared. So I'm going to enter that in. Okay, so I get 1.33 or 4/3. Okay, we're also told that the balloon is rising at 80 feet per minute, so we know that's dy dt, or dy dt is positive 80. So now I can just divide that 3/4, that 4/3 over and solve for d theta dt. So 4/3 becomes 3/4. Okay, so I get 0.2. And theta is in terms of radians, time is in terms of minutes, so radians per minute. All right, last one here, number 8. We have a function that is differentiable on the interval from 0 to 10. So it's a smooth curve. If f of 2 equals -5, f of 5 equals 5, f of 9 equals -5, which of the following must be true? I think it helps if we just sketch this graph out. So I have 2, -5. I have 5, 5. And then I have 9, -5. We know it's a smooth curve, so I'm just going to create a graph that goes through those points. Which of the following must be true? Okay, so no matter how we draw this graph, it must hold true. Function has at least 2 zeros. That is true, right? There's no way that we can ever create a graph where everything is connected from one point to the next without hitting our graph at least twice. Maybe it's more than twice, but it's got to hit at least twice for us to reach that point and back down again. So we know this is true. the graph has at least one horizontal tangent line. That is true. Here, this may not be the max, but the graph has to go up and come down, and it's a smooth curve. So if it's going to make its way down, this is basically applying Rolle's theorem. Rolle's theorem says if I have two endpoints that are the same y value, it's got to be able to go up, go down, come up, or go up, come down. And along that path, as long as it's a smooth curve, it's going to have to slope 0 somewhere in between. So true due to Rolle's theorem. And then for some value c between 2 and 5, we can guarantee a y value of 3. And we see there's no way that we can draw this graph without hitting a y value of 3 somewhere. Right? The graph has to cross through that y value of 3, and that is basically IVT. If I have 1 point below and 1 point above 3, and the graph is continuous or continuous, then the graph has to cross through. So we know all 3 statements are true. So answer choice D. All right, see you guys at the next review.